I guess we'll get started. Apparently there's some people who aren't good in the morning. I wouldn't know anything about that. Okay. The original brief I was given for this talk was that we would go through basically the process of getting data from a form of raw data in Quizz or some other software into an analyzable format. And as I started making slides to do this, I realized that there is so much background knowledge that's worth prefacing that I've tweaked it slightly, so we'll still get to go through the example project, and I've still put those data and commented scripts online. But I also think that there's some important preface information that's worth going through too. So I've titled this broadly as the principles of data processing, but these are basically bits of information that come from different sources in terms of best practices for data management and for data processing in general. So the first thing to say is, why should we care about pre-processing or processing of data? Surely it's just a means to an end, and that is true, it is. But we deal with all kinds of data all the time in psychological research, as most of you guys probably know. Even the specific software that we use to run our experiments changes, sometimes from month to month even. I personally, during my PhD, went through about 6 or 7 different kinds of experimental softwares for different things like, oh, you need to do mess tracking, you need to do whatever, different requirements, different softwares. This also means we get different forms of data. And different softwares differentially manage data. So some softwares, like in Quizz, will give you data that are in a relatively tidy format. And tidy is actually a technical term that I will explain in a couple of minutes. But you also get data that look like a gigantic uninterpretable mess. If you get data out of a JSON file, for example, if you run studies online, if you were a human being, you're not going to be able to read that. So what we need in general are reproducible and generalizable workflows. We need basically broader principles for how we approach data processing that we can apply abstractly in different contexts. So this is kind of funny because the one consistent thing of basically every psychologist, especially experimental psychologists, is that we need to process data. But basically no psychologist gets any formal training in how to do that. We get formal training on analyzing data, formal training on methodology and things like this, but in terms of this pipeline, this kind of middle part that takes us from our experiment to our results, it's kind of a bit blurry. So it's funny, especially in comparison to industry, where having consistent workflows across a team or across an organization is really, really standard. So we don't get formal training in things like how to structure our folders or our projects. We don't get any formal training really on version control. With the Open Science Framework, a little bit more, but with things like GitHub, we do hear about them. Some of us do learn about them, but it's rarely in a formal training context. And we'll talk about version control if we get time, but I'm going to mainly focus on the issues of folder structuring or project management, project organization, and tidy data, that technical term that's popped back up again. So I'll explain again what this means in a moment. But it's important to say that these are just integral to reproducible workflows and generalizable workflows. Also, if you know an abstract formula to approach the organization of projects in a clear and reproducible way, then you're going to save yourself a lot of time in the long term when you are given a new type of data or a new type of project and you're unsure of how to approach it. Okay, so last night I realized it might be fun or funny to do a bit of a quiz to start off. So could anyone tell me where in this data set, and this is a real data set from an OSF repository of a published paper, so if I wanted to reproduce their code or analyses, this is what I would get. So coming in completely dry to this, can anyone tell me where I can find the processed participant level data? And what I mean by that is the data frame or a CSV file that has participants as rows. So row 1, participant 1, and that might give me information about like a mean IAT score, gender, age, and so on. Can anyone tell me where I can find that here?
We can't see it.
Well, then you definitely won't be able to tell me.
Looking at the slide.
Yeah. If you can look on your computer, if it's too blurry.
But
Data final.
But do you think it should be in data final here, or data final 1, or data final 2, or data final 7?
Data final 7.
Okay, I'm not gonna lie, I didn't check. I assume it's in data final 7, but I'm not sure. What I'm really curious about is what happened between data final 3 and data final 7. There must have been something crazy going on here. I say that facetiously, but there is a genuine question here. What is going on? Why are we going from 3 to 7? What is data final? Why are they all called final? This isn't a PhD thesis. You don't get to iteratively call it final and final and final. At some point, you need to have your process data. So, yeah, I'm pretty sure it's in data final 7, but also, to be honest, when I look through these different scripts, and look, we've got 6 different R scripts here, all lumped in together that range from data cleaning ratings, all the way up to meta-analysis. All in one folder, along with a bunch of data, all of which I can't tell which is the raw data, what's the process data. It's a mess. And that's not an evaluation. It's just technical. It is a mess. It's very hard as a novel viewer of this to say what is what is where. And I think, at least for me, when I started my PhD, my data, if it looked like this, I would have been happy because mine was even messier. Because we don't get much formal training in how to do these things. And I'm sure most of you probably are looking at this and thinking, yeah, my data has at some point, or maybe even currently, does look like that in some of my projects. That's not a bad thing. It's just not an ideal thing. As you can tell, because nobody knows where to find this data file. Let's go to round 2. This is from another published project, which I downloaded from the OSF. So the 2 relevant folders I've downloaded. Now, the names are quite long. I personally consider that problematic too, because I think that folder names should be inherently clear and informative. So I tidied them up a little bit to give a bit of help. So, can anyone tell me where I would be able to find the processed participant level data? Let's do a bit of a, like one of those old style, like Bandersnatch games. So, which way do we go? Do we go to raw data or to analysis? Analysis, okay. So we're going to skip through raw data, which is right and good, which tells us these folder names are informative at this level. Okay, so now we've got analysis. And what I see here are, there's 1, 2, 3 CSV files. One's called all okay, one's called mem okay, and one's called z all okay. There's a text file, which is called Markdown IAT script. There is an R script, another R script, and another R script. Can anyone tell me where I can find the processed participant level data?
No.
I would go to the R file and check what happens at the end.
Okay. We could do that, but actually, you could do that. It's funny because when I open these R files, there's another problem, which I wanted to get to a bit later, but it's that all of the directories in this script are relative. So they're old, or sorry, I should say absolute. They're old directories from the lead author's computer. So the paths don't work when I open this project on my machine. So I can't even read these data in without having to tweak it. Now, if we're talking about reproducible workflows, at minimum, this is really annoying to do. And at maximum, we actually might lose some information that could completely eliminate the reproducibility of the project. But the idea of being able to do this in 1 or 2 clicks, not possible. If you've got to go into the script to find out which is the data, the finalized process data, that's a problem because I should be able to tell just by looking at this. Now we're all of a sudden putting more barriers up to reproducibility, more barriers up to being able to engage with this project as neatly and as cleanly as possible. Okay, now, round 3. And as we know, the third one is always probably the good one. So, find the processed participant level data. Where do we go from here?
Analysis.
Analyses or data? Oh, interesting.
It's the analysis.
Someone put their hand up if they want analyses. Put their hand up if they want data. Okay, well, data is the right answer. But I can see why you would say analyses because actually, in my opinion, the logical place for the data to go are in the folder called data. But so often we conflate the presence of our data with our analyses. So it's normal that we might mix them up, or alternatively, it's just not ideal organization. We can just disagree, and that's okay. Okay. So we're in the data folder. Where could I find the process participant level data? where do I go next? We've got 2 Markdown scripts, we've got 2 HTML files and 2 folders, one called processed and one called raw. So where do we think it is? Processed, okay. And then in processed, we've got 3 files. One is a code book for the data, which is basically an Excel file that describes the data. One is a CSV file called participant level, and one is a CSV file called trial level. Where is the processed data? Yeah, exactly. So, barring a slight disagreement on the top folder, I think we can all agree that this is probably the easiest one to find what we're looking for. And you might be saying, okay, well, you did use the words processed and participant level, and the files and folders were called that. And that is true, and yet this is the point. They were named clearly. I had a specific query, and I was able to follow that query really, really easily through this list. So, importantly here, there's also folders that distinguish between other features of the study. If I wanted to find the materials or measures used in the study, I would know where to look. If I wanted to find the pre-registration, I'd know where to look. If I want to find the analysis script, I would know where to look. If I wanted to find out where the raw data was, I know where to look. The structuring of a project like this is critical, because if I am coming from the Open Science Framework, I download some data, and I see something like the example 1 here, I go, how do I even begin with this? And suddenly I'm scraping through scripts just trying to figure out what these files mean. Ideally, you can even have a code book like this that will just tell you that you can refer to it and say, okay, now I know what everything is. So there are intuitive ways and non-intuitive ways to organize a project. Boring things like folder structure are really important for reproducibility, and that's the point I'm trying to illustrate here. So given that, what is an ideal folder structuring within psychological research? Kind of hard to say, and there are no uniform standards precisely because we don't get formal training in this. I was at SIPS in 2019 in Rotterdam, and they had this basically initiative that they started called PsychDS, Psych Data Storage or Data Science. And the idea was basically to try to formalize this. It's still in the process, and actually if you're interested in contributing, they have an open Google Doc that you can contribute to. But this was an initiative that was set up for that. The general rule, well, there are a couple of general rules that people seem to agree on as best practices, but in my opinion, one of the most important ones is having this distinction between data and processing in one folder and your analysis in another. So keeping the pipeline of going from raw to processed data in one side, and then on the other side saying, and now given this, we can keep our analyses separately. So this is really hard to see, but take my word for it that, okay, actually I think I should have another figure for this. Okay, so basically an ideal structure, or at least a very useful and intuitive structure, is something that looks a bit like this. So you start off with a main project folder, which tells you, okay, what project am I dealing with? Then you have individual folders for each, say, experiment, or maybe a separate folder for your meta-analysis, basically things that involve processing and analysis, and maybe even separate data files separately. Within that, you distinguish between data and analysis, and then maybe other things for registration, measures, a manuscript, etc. And within data, we've got 2 distinct categories of data, which are the raw data and the processed data. We also can have our R script, which basically moves us from here to here. And within those folders, we have multiple different files, usually for raw data and also for processed data. Now, ideally what your analysis script will do is it will come up here, across here, down here, and into the processed CSV file. That is contingent on being able to do that across different machines. Ideally, what we want to be truly reproducible is that I can go onto the OSF, I can download a project, and I can need 2 clicks to reproduce everything. 1 click that says run the processing script, and 1 click that says run the analysis script. A good way to achieve that is to use our Markdown. So I think I should, yeah, okay. So let's say what our Markdown is. It's a combination of an R script and a Markdown file, which is basically kind of like a word processing coding language. But the main point about our Markdown aside from the fact that it gives us a way to structure our code better, which I'll explain in a moment, is that it uses a relative working directory. So if you've opened a script that looks from someone else and you see that the data are loaded in like this, you go users, Jamie Cummins, Git, AMP awareness, experiment 1, data processed, and you get a directory like this. Of course, once you get to Jamie Cummins on your machine, then you're not going to be able to find the file. With our Markdown, you use basically what's called a relative working directory. So the Markdown file knows where it starts. The Markdown file knows that it is here. So what I need to tell the Markdown file is go up one level, go to the folder called data, go into the folder called processed, and go into this file. This is a lot handier than specify. Sorry.
No, I just wondering, can you actually go up levels? I've never been able to.
I will show you exactly how to do that because it's a good question. I'm going to just type it in because I haven't put it in. I meant to amend it. So yeah, the way you go up a level is really simple, and you basically do something like this. So read underscore CSV, and then let's literally start in analysis and let's end up at processed. So we're in analysis. What we do is we do ... and that, oh well, is that 2 dots? Yeah, ... and that means go up a level. So ... then go to the folder called data because it's on the same level as the level above where the script is. Then go into, yeah, well then it's just a normal directory, and then processed .csv, like that.
Oh, and this only works for our Markdown and not for standard R files.
It should, as far as I know, it should also work for standard R files.
Oh,
So 2 points means 2 levels, right? ...
is 1 level.
Okay.
So if I wanted to go up 2 levels, then what I would do is I would repeat ...
Okay.
Think of this it just basically means go up once. Sorry.
No, it's okay.
To also say, like this, of course, it's not that you can only use relative working directories in our Markdown. In principle, you can add code to the start of an R script that does this too, but it's not integrated in the script by default. When you combine that feature along with the usability and clarity of our Markdown, in terms of reproducibility and clear code, I think that this is a much more viable and useful kind of approach to writing code. What it is really basically is very, very similar to a normal R script, except you can also have a couple of extra features. So firstly, if you want to open an R Markdown file, you go up to the little thingy in the corner where you normally, in R, where you normally use to open an R script, which is the top option, and you just go down 2 options and you click R Markdown instead, and you'll immediately be given this. So let's go through this really quickly. What do we see here? The first thing that's different is that it gives this kind of title, author, date information. You don't get this by default in an R script. This can just be handy to give clarity and context to what this is, what it's for, and when it was done, and who did it. The next thing you'll see is this, basically these 3 kind of dashes, these squiggly brackets, some stuff in the middle, it closed, some code in the middle, and then these 3 dots that are basically closing the thing. This is called a code chunk. And a code chunk, you can approach it differently. I kind of like to think of it as like a paragraph. So this is like a paragraph for your code that says, I'm doing something here, and now I've finished doing that thing. Compare this to when you use an R script, and it's very difficult to kind of make clear sections. People often use like a bunch of hashtags or different kind of symbols and things like that, but it's not as inherently clear as this is. It's really changing the background color. It's saying something is happening in here and now it's done. So you can put as many lines of code within a chunk as you like. It just so happens that there's 1 line here. But what you can basically do outside of these chunks is also important. You can add these basically text information. And yeah, so you can see that there's like 2 hashtags that are done here, which basically means a level 2 heading. Then there's just a bunch of text, which is just read as text. The R script doesn't see it as code. And what this means is that you can literally write as much as you want and give as much context as you want about the code that's coming afterwards. So I have a title for what this chunk is going to do, and I have a description for what it's going to do too. I wish I could go through this in a bit more depth, but I want to keep the pace up. But basically, there are other cool things you can do with Markdown in addition to it being better for reproducibility and coding, which includes being able to knit the Markdown file to a HTML file. So if ever you've gone online and looked at tutorial blogs and things like this for R, the odds are that there's about a 50% chance that it was done in our Markdown. So basically, you click knit up here whenever you want to do this. It'll give you this drop-down menu. You can choose any of them. I've just selected knit to HTML in this case, which would be what you would do if you want to upload it. And then if you open that file after it knits, it'll open up in the browser here on your local machine, but of course it's an HTML file. You can just put it online. And basically, it'll give you this kind of report-style format. This is useful for anything that ranges from giving a report to your supervisor to writing an actual blog post that you want to upload and make public. Especially because you have this integrated with Markdown, which means that all of the rules of Markdown apply. Things like using these hashtags to indicate a double heading, or using 3 of them to indicate heading 3. There's a bunch of other stuff that, 1, I don't have time to get into, and 2, I'm not aesthetically minded enough to go into because I'm terrible with this kind of styling. But all I can say is that you can make really, really nice pages using this, and also that helps with reproducibility, because if I don't want to rerun a code or something, I can open up the knitted Markdown file that goes in the project repository and just look through it like a report. And also you get all of this nice kind of narration around it, so I'm not just reading ugly code comments. Okay, so I hope I've convinced you about that. Well, okay, it's all right time. Next thing I wanted to mention is this idea of tidy data. So, tidy data is a technical term that basically refers to data that abides by 3 specific principles. It was kind of forwarded in various iterations, but the iteration that I'm sort of looking at or talking about here is the one from Hadley Wickham, who's basically the main developer behind RStudio. He's also just a coding genius, and if ever you want tips on R, just go onto Twitter and follow him, and you'll learn something new literally every day. I wish I was exaggerating, but I still learn stuff every day from looking at his account. So what is tidy data? What are the principles behind it? They're very simple. The first is that every column in a data frame needs to be a variable. Every row should be an observation. And every table should be an observational unit. I think these first 2 points are relatively clear, but the third one is probably a bit vague. Like, what do we mean by an observational unit? Basically, what we mean by that is that there is a distinction between, say, for example, participant-level data and trial-level data. An observational unit in a data frame that has each observation or each row as a participant means that we're situated at the participant level. If we have that information, we probably don't want to also have trial-level information where we have multiple iterations of each participant, because then it's not participant-level data, it's trial-level data. To make that a bit more concrete, if we have an IAT file that's say the trial-level data of the IAT, we probably don't want to have the demographic information for each participant in that file. It's not ideal because we probably also want to have another file that summarizes data for each participant. And if we have this trial level data, we've got a column that's just repeated 100 times for each participant with the exact same value over and over again. And I mean, I still do it sometimes when I get lazy, to be honest. But it's not tidy. It doesn't follow these principles, and that means that there is an excessive amount of information where there doesn't need to be. Particularly because you probably end up processing the demographic information when you use the participant level data file. So it's really superfluous within the trial level data file. And the last thing with that is that if you have this trial level data file, when you want to say get a count of the number of the different genders in the study, you probably need to do some processing before you do that. So you might want to run like a function that says return only the distinct values or return one value per participant. So in that case, just use the participant level data file. Okay, so a couple of examples for these. For every column is a variable. Here's a good example. I think this is good to illustrate. Here's the difference between messy data and tidy data. In this messy data example, you've got different observational units in the form of different religions. And then you have got a bunch of columns here. The columns aren't clear what they mean, basically. So you've got less than $10,000, $10,000 to $20,000. There's numbers beside them. I don't really know what these numbers mean. I kind of infer from the structure of the table that they probably are count data, the frequency, but it's not clear. And if I want to analyze this in a regression or something like that, then I'm going to need to restructure this, because how can I tell the regression? Well, what can I tell it really? It's going to get confused, even the LM function. So it's just messy. It's not inherently intuitive about what these numbers mean. We can do better. Compared to this tidy data here, where we have the different religions, but now iterated to reflect the different levels of the variable income. This is one of those things where the observational unit is repeated, but it's repeated only because it's the tidiest way to express the different levels of this in the most interpretable way possible, because we need this third column called frequency in order to contextualize what these numbers actually mean. So every column is a variable, and the column name is informative as to the content of the rows. Does that make sense? Okay. For the issue of the observational unit, this is just another illustrative example. So here we have this messy data table or data frame where we have the year of song that was released, the artist of that song, the length of time for that song, the track name, the date. Okay, but what do we mean by date? I actually do know, but I'm kind of trying to explain it, and as I'm explaining it, I'm going, oh, this is hard to say. What this reflects basically is its position in different weeks of the Billboard Top 500 tracks. So what we end up with basically is the same track repeated multiple times per week based on its different ranking in the Billboard charts. But I don't need all this extra information. I don't need to see the time, whatever this is, 7 or 8 times. I don't need to see the artist. We just need to know the week, and we don't need extra information. We just need one column that tells us what this song actually was. The way we would approach this is that we would separate this into 2 different tables. One table that focuses on the information about the track itself, the time, the artist, and so on, and another table, a separate table, which details the Billboard rankings across the different weeks. And we would just have basically a single identifier that links these 2 tables together. If anybody has had experience with using SQL or SQL, then this will be very, very familiar, because in SQL, this is exactly how data are organized across multiple different tables, with this kind of consistent identifier or identifiers. So if ever you want to move into industry, SQL is a big databasing language, and this principle applies also to the organization of SQL. Okay, so I hope I've convinced you on this, and if not, I would highly, sorry.
Suppose I have in mind another possible way which could be targeted at practice messy. What about if you have one column for each week? For one row is 2 pack, but then I have week 1, rank 87, week 2, rank 82. So as a columns, instead of being 2 different data files, it's a single data file. Would that be messy, tidy, or somewhere in between?
It probably depends on your no, I would say it would be messy, actually, because I would say that would be kind of similar to this.
No, because they are repeated measures. It's not. So what I mean is that structure would be the structure. For instance, if you do some kind of repeated measure analysis, you can check for the same variable at different time, which means it's a different variable, but it's unique.
Yes, it's the same. It's the same.
I would need to sit down and look at it, but it could be tidy. I think, and then in that case, it depends on the analytic strategy that you want to take. Basically, do you want to say I don't know, compute a t-test between week 1 and week 2?
Just a kind of trend line or whatever.
Yeah. Indeed. But even then, I think that the data can still be expressed in this kind of long format. And I would need to think about it, is the answer. I can see problems already emerging, though, where you will have, say, 50 weeks, and there are songs that are that have rankings in the first 25 weeks, but not the last 25. So then there are 25 columns that are basically have empty values. It's basically, that's harder to deal with then in terms of filtering that out. Yeah, purely in practical terms, I can see that the analysis that you would subsequently want to run would find that more difficult and involve more processing than just having this as a single column. But what I would say as well is, and say this to everyone too, if you have questions like that, read Hadley's paper, because honestly it is so good. It explains everything super clearly, better than I can, and it's very, very informative. It changed the way that I approach data, and it's really cool. Okay. All right. So theoretical stuff a little bit aside, let's move to practicalities. How do we do this in R? How do we approach it in R? Fortunately, there is a whole collection of R packages that you've probably heard of, even if you don't use it extensively, called the Tidyverse. And the odds are you're probably already using at least one of the packages within this collection of packages, ggplot. ggplot, the GG stands for Grammar of Graphics. It's basically a tidy approach to plotting. So if you have used ggplot, then you're probably already familiar with some of the kind of tidy approach. The main processing package within Tidyverse is dplyr, and you've probably used at least one function from dplyr in the past. So dplyr is, as far as I know, the basically next generation of the old plyr package, and it's basically incredible for manipulating data. It's I think unparalleled within the R universe as a package. So important thing to know, as I think people probably are already familiar with, the Tidyverse collection of packages can, maybe it's incorrect to say that they have their own syntax, but certainly there is a specific style of coding in terms of the Tidyverse that is different from base R. So, for example, if you wanted to select two columns from the data frame called crime.ny 2005, and you wanted to select the type of crime and the count, this is how you would do it in base R. I literally can't explain it more than that because, to be honest, I don't know that much base R because I program almost exclusively in the Tidyverse style. That's a limitation on my part. But you would do it in this way in base R, and in dplyr or Tidyverse you would approach it in this way. So why use one over the other? Most of the time it's because you just learned one when you started coding. I would advocate for using the Tidyverse over base R because I think that its structuring, syntax, and approach are generally more intuitive. There are collections of packages that all integrate very well with each other. And dplyr in particular for data processing is just super powerful, and you can do in one line what requires 10 lines in base R. So the functions are simultaneously quite succinct, but also very powerful. So probably for those of you who haven't used Tidyverse before, or have kind of seen it but not really engaged with it too much, the first thing that you'll think is, what the hell is this? What is this little, the 2 percentage signs with the greater than sign in the middle of it? And I think it's a bit menacing to look at, but basically it's called the pipe. So what the pipe does is, and I think it's useful to think of code in terms of language, so code chunks in our Markdown are like paragraphs. The pipe is a phrase that means and then. So we have kind of equivalent pipes that are used less in base R. I think there's like the 2 straight lines and the sign or something, but anyway. And then is what the pipe means. So I get to write this sentence in my code within my paragraph, where I say, take the data frame called df and then select these three columns called participant ID, gender, and IAT score, and then group by gender, and then summarize a new column called mean, which is equal to the mean of IAT score. This is, for me at least, very, very useful and clear. Once you see that this means and then, everything else kind of opens up. Now I'm writing sentences in code. I'm saying do this and then this and then this and then this. In base R, I think that you often end up creating a lot of superfluous or excessive data frames that you say, okay, well, you know, here, for example, okay, I'm going to assign the old data frame to this new value, and then I'm going to do some more stuff to it. With the pipe, you don't need to do that. You can do every set of operations within a single set of code and then assign that to a data frame. This doesn't mean that you completely omit all of the excessive data frames. You're still probably going to have some, even just purely based on the fact that we write code sequentially and then go back and fix our mistakes and things like this. But it definitely reduces it. And when we can say and then, it opens up a whole different world of coding. In the same way that in ggplot we can use the plus sign to mean and then add another geom, add this, add that, add that. Of interest, and I saw this in a talk that Hadley Wickham gave online somewhere, the plus sign in ggplot was also meant to be the pipe. So in ggplot when you use plus it should be the pipe. But one of the developers basically screwed up and forgot to use the pipe, and so they haven't ever fixed it since then because it's just become convention. I think the plus actually kind of works for plotting specifically well. And of interest is that imagine I wanted to plot this mean column after I've created it. I could use the pipe, and then I could run the ggplot function directly after the pipe. And then I can do all of my ggplot stuff in the same code chunk. I just need to remember to substitute the pipe with the plus sign once I get to ggplot.
I see a difference between the use of the plus in ggplot and the pipe. So the pipe just flags the element before the pipe as the first argument of the element after the pipe, whereas the plus does a different thing, so adds layers. And what you pass to the next function is not necessarily the first argument to the function.
True, it's not completely linear, but at the same time, what it is ultimately doing in the background is creating a list and then just manipulating that list. Because the plot object is just a list with a bunch of other arguments. So you're right that it's not like a one-to-one mapping, I guess, but it's very it's very similar.
Yes.
Yeah. Okay. So yeah, just to say, like, read this. It goes take the data frame called df, then select 3 columns, and then group them, and then summarize them, which I think is very clear. So just to give kind of an example, I'm sorry if this is tiny. There are 4 steps here, just to show you this kind of in more detail. I'm creating a data frame called df. It has 3 different columns. One is called participant ID, which just has values ranging from 1 to 20. A column called gender, which just randomly samples from male and female 20 times. And an IAT score, which is just basically arbitrarily sampled from a random normal distribution. Then I look at the data frame just to see what it looks like, and it looks like this. It has 3 columns. When I run this, it's funny because I should have actually made 4 columns because the select function here is going to do nothing because it's just choosing the columns that are already in the data frame. So basically, you could do all of this without having the select function there. I just didn't conceive this very well. And then I go group by gender and summarize the mean. What I end up getting at the end is a data frame that has 2 columns and 2 rows. The columns correspond to the 2 variables that I specified here, so gender and mean. So I get the basically the different genders and the means for those genders. I'm going to go into more detail in a moment on each of these different functions separately and describe what they do. I hope that it already is kind of clear here what this group by summarize combination is doing, but I'll give a bit more information about the specific operations applied. Actually, basically now. Before I keep going, does anyone have any questions about anything that I've said so far? So for the rest of this, what I'm going to do is I'm going to explain what all these different functions do, because these are kind of the main functions you use in, from dplyr in the Tidyverse. They're by no means exhaustive. There are literally, I would say, thousands of functions that you can potentially use. But when I look through my processing scripts and the processing scripts of others who use this universe of functions, these make up maybe 50% of all the functions that are used. Okay, after that, I'm going to open up a practical example and we can run through it together, which is the one that's on the Open Science Framework. Okay, so firstly, select. We've seen this one already. What does it do? It takes column names as arguments, so column names that are within a data frame that is referenced. It selects those columns which are named and drops all other columns. So if I have a data frame that's called df and I say, yep.
Just for clarification, it only selects the columns and creates a new data frame, because when you say it drops all other columns, I would understand that it deletes it. I wouldn't be so happy about it.
It doesn't delete them entirely. So basically, a new data frame is only ever created if you tell R to do it. So you start off by running the operation by assigning this to a data frame.
Okay.
So it's not that it's inherently changing the data frame. It's not like, say, in Python, for example, where sometimes you can run an operation on a data frame and it just changes that data frame for good. You still have the original data frame saved from prior to that in your within the, oh god, what's it called? Well, anyway, in the project.
It selects the columns and ignores
Yes.
the other existing columns.
Yes.
Okay.
Yeah. Exactly. So if I say select and I say just select age, comma, gender, it returns the columns age and gender. It doesn't inherently assign it to anything, only if I tell R to do it. Yeah?
Another question. So let's just say I have a data frame that has column A, B, C, D, E, F, G.
Yeah.
And I want to create a new data frame with some of the columns, but in a different order.
Yeah.
If I select them in the order that I would like to be in the final data frame, then it would use this, because if I say select B, D, A, C, then the new data frame would have the columns in a different order.
It will return the columns in the order that you've selected them in.
Okay.
Yeah. Sorry, I wanted to open the terminal. Okay, now. I was going to open the terminal and just show it, but then it's too small and then I couldn't get it back. So yes, it's also ordered, which of course can be very helpful, because if I want to see participant and demographic information first and then blah 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 blah, then yeah, you can do that. What you can also do is you can select via negation. So I can imagine I have a data frame with 100 columns, but I want 98 of those columns. For whatever reason, I've got 2 that are just excessive. So if I want to do that, then I can just use the minus sign to say, okay, we'll just select minus extra column 1 and minus extra column 2. What this will do is it will return my data frame with all of the columns except the ones that I've specified. This is pretty handy. I wanted to leave it to the end, but I can also spoil the surprise now. If you select, say, a column, and then you say, imagine I have a column called age_response. It's come out of Quizz like that, which sometimes happens. Imagine I want that column to be called age instead of age_response. What you can do then is you can, within the select argument, say select age is equal to age_response. So what that's basically doing is you're selecting the column age_response, but also assigning it to a new value called age. So now you'll get that column returned with a new name instead, the one that you specified on the left-hand side of the assignment operator, or the equal sign, which is also handy and cool. And you can also use indexing. So if you say select 1 to 3, then you'll just keep the first 3 columns. If I've got that indexing wrong, it's because I also code in Python and use indexing more there and never use it in R, so don't hate me if it's not right. I hope you understand the rhetorical point. Okay, so the next function is filter. So filter is kind of like, if select operates on columns, then filter operates on rows within a specific column. So you can use this to keep only rows in a specific column or set of columns if you apply multiple arguments to it, where the column or columns values conform to specific values. So it's even simpler than it sounds. If I take my data frame and I say, okay, well, filter gender is equal to male, then what this is doing is it's going, okay, take the data frame and then filter the column gender so that I only return values where the column called gender is equal to male. And importantly, only the string male in this case. So sometimes it will figure out what type you want, but usually you need to just, if it's string, put it in quotations. And you can also use negations. So you can say, take the data frame and then filter the column gender for everything that is not equal to the string male. This will give me back my data frame with everything except those entries where gender is equal to male. You can also add, Boolean operations, so you can say gender is not equal to male and age is less than 35 or something like that. So this is also a very powerful function for operating on data, and especially if you have, say, IAT data, where your critical blocks are named something like you have some column that's called block type, and it's called either critical or practice. Then you can say, we'll just filter out all of the practice ones, either by saying filter block type is equal to test, or filter block type is not equal to practice. So very, very powerful way of getting rid of this stuff. Again, just to reiterate too, it's not that these approaches and options for processing don't exist in base R. As you all know, of course they do. It's just that Tidyverse provides this kind of collection of grammatically identical functions that all integrate with each other very well. Yeah?
Yeah, I wonder, instead of having the sign equals,
Mm-hmm.
so like only the rows for which you have this exact value, can you use the like the percentage, percentage stuff?
I don't use that one, but I think I know, I can probably figure out what it is, because it's probably similar to like percentage in percentage.
I don't know, I found, because I use the data table, this kind of functions, and in data table you have the like.
Is that
basically it's looking for values that are similar to the value that you define after, so not perfectly equal to that. Like for instance, for the male stuff, you have
a capital M.
capital, or like 2 L's, I don't know. So you're looking for some stuff that are, and it can be useful, for instance, if you have an open-ended format, or recipient just write themselves.
You can definitely you can use the like function, or you can definitely use that within this. Anything that you can use in base R or data table, you can use in it. Yeah, sorry, I got too bogged down in figuring out what that actually did, but indeed you can. Yeah, you can also use like Stringer, which is another Tidyverse package in R, which can do similar things. But yeah, like would integrate perfectly. Okay. So moving on, we're going to also look at mutate. So mutate is probably the most common one that you will use in general. So what mutate does is it either creates a new column or changes an existing column based on arguments that you provide. So for example, here, if I go take the data frame df and then mutate a column called gender, which is equal to, if gender is equal to male, then 1, and if not, then 0. So just a context on what this function here is, it's if else. Basically it's saying, if the provided argument, then return this first value, and if not, then return the second value. So what we're doing here is we're saying, within this data frame, look at the existing column called gender. if gender is equal to male, then this column gender is now equal to 1, and if not, then it is equal to 0. It's basically recoding the column in this case. But the cool thing is you can mutate multiple columns at once, and you can do this very powerfully. So for example, I can also say take the data frame and then mutate the column gender, doing the same thing we just mentioned, and then comma, then another column called age_over_35, which is equal to if age is greater than 35, then 1, and otherwise 0. In this case, age over 35 doesn't exist in the data frame before you do this, but afterwards it does, and its values are contingent on this provided argument. Okay, there's also another thing to mention, which I think is that most people in base R use if-else. I'm not sure how common case when is. So, have you ever used if-else and you end up using like multiple nested if-elses? So you want to say, or at least let me put it this way, I did when I started coding. So you start going, okay, well, if else age is less than 20, then it's equal to 1. And if you want other conditions, then you've got to go, okay, and then the else argument in if else is another if else statement, which goes, so, okay, if age is less than 20, then 1, and if not, if it is less than 30, and it's greater than or equal to 20, then 2, and then. So here I would want 5 levels, which means I need to do this 5 times, and it's so time consuming that I literally was not bothered typing it in the slides. Alternatively, what you can do is you can use this function called case when. By the way, you can also use this outside of mutate. It's just a handy function in general, where you basically, okay, mutate this new column, which is equal to case when age is less than 20. So first condition, use the tilde, and then you say what you want the value returned to be. Then you give the second condition, tilde, the value you want returned. The third condition, tilde, the value you want returned, and so on and so on and so on. The very last argument, which is basically the equivalent to else here, which is after everything, what do you do with anything that doesn't fit these provided values? You just say true. Because what this basically does is it just checks if true in general, which will always be returned. So then you say true, then 6. So what this is doing is it's basically going, mutate this new column based on a bunch of these different values, and then at the very end, if there's anything left over, then just assign it to the value of 6. It's just a tidier way of coding compared to this ugly if-else approach. Okay, I'm going to try to speed up. So, summarize is very, very similar to mutate, but it does 2 things in addition to what mutate does. The first thing is that it drops unmentioned columns within the function. So if the columns haven't been mentioned within the function or within a group by argument provided beforehand, then it drops those columns. And then it returns only unique values that have been basically computed. To illustrate that more clearly, here I say, and I guess it's probably hard to see, take the data frame and then mutate a column called mean_age, which is equal to the mean of age. So here I'm using the mutate function. And what happens is I get all of the columns that were already in the data frame, and I get a new column called mean age, which is the one I just mutated, which is equal to the mean of age. So that means I get this same value multiple times for each entry in the data frame. So I have the mean age, which is the same 20 times. Now, sometimes you just want to get the mean age. You don't want it to be iterated across the data frame. You might want to just output it as a table or something in a report. So to do that, what you do is you just change, you keep the exact same syntax, except you change the function from mutate to summarize. And when you do this, what you'll get is a single value, which is the mean age. You'll notice it corresponds perfectly to the one that's here. But it's just not repeated, and I lose all of the extra columns that I wasn't interested in. You might remember also that summarize, I integrated it before with group by to get the mean age for 2 different levels of gender. And this group by function is very powerful for that. It doesn't really do anything by itself, but it integrates really well with these other functions. So for example, here, Again, it's hard to see, but I'm basically going to take the data frame df and then group by gender, and then mutate a new column called mean age, and that's equal to the mean of age. So this is exactly the same thing to what I was doing here, except now I've got a group by before I do my mutation. And you also can't see this, but basically what you've ended up with here is that there are different values in mean age when the gender is male compared to when it is female. So the male mean age is always 39.4, and for females it's always 49.8. So it's still iterating over the whole data frame. It's not removing any superfluous information, but it is giving different values based on this grouping column. And that can be very, very helpful. The last thing to say is that whenever you use group by, after you've performed the operations you want to run on the different groups, you should always run the ungroup function afterwards. Because otherwise, especially if you save this to a subsequent data frame, R remembers that you want these data to be grouped. And so somewhere down the line, if you're running an analysis or another kind of part of processing, you might start finding that the code starts acting weird and you don't know why. And it's because R still thinks that this data frame is grouped by whatever the column is. And then it basically gets confused. So you group by, you do the stuff, and then you ungroup. Rename does what it says on the tin. Very, very simple. You take the data frame and then rename, and the new column name equals old column name. So if you've got multiple columns you want to rename, you just feed the new column name equals old column name for each of those columns. And like I already said before, it integrates with the select function in this case. So this style of renaming can work within select, where you say select the column participant ID, and it is now called subject. In this case, this would select these three columns, and it would rename the old column participant ID to subject. Okay, I feel like I've listed too many functions here. Distinct, what it does is it basically takes columns as an argument, and it returns the data frame with only the unique combinations of those columns. So take here, for example, I have, what do I do here? Okay, so I have a data frame here, which is actually in Quizz data, with a bunch of values in it. And if I say to R, take distinct, what do I say, subject and trial code, then what it's going to do is it's going to basically return the distinct values for the combination of subject and trial code. In this case, it's actually not losing anything because there are only 2 entries per subject and 2 different values of trial code. But what it will do is it's dropping the extra columns. So it's only returning subject and trial code now and nothing else. This can be handy if you want to start summarizing some data or something and you've got a bunch of columns you want to select out. Now you don't even need to use the select function because you're basically integrating that select within this distinct function. What else to say about this? If I had said distinct subject block code, because block code only has 1 value, I would basically only get 1 row per participant here. So I would lose a bunch of information that I probably wouldn't want to lose in this case, but in other cases I might want to lose. Okay. You can also add this argument dot keep all is equal to true with distinct. If you do that, you basically keep all of the extra columns. So that can also be handy for different contexts. Okay. Count, good for providing descriptive statistics of data. So for example, data frame and then count will return the total number of rows. If you're reporting this, or you just want to get the, say for example, the total sample size, this can be handy if you do it on your processed data frame. If you add specific column names as arguments, then you can count along the different levels of that argument. So for example here, this would return the number of participants along the different levels of gender. And it's basically equivalent to going group by gender and then count. Okay, I'm going to skip these, but you have them in the slides. And I'm going to move on to the practical example where we have 20 minutes to basically explore this. So with this practical example, excuse me, what do we have? We have sample data from an actual EC study that was done in a Quizz. So these data are actually simplified versions of data that I showed earlier from the second question in the quiz that I gave. So basically the simplified procedure of what was done is that we get an evaluative conditioning procedure, participants then complete an IAT, and then they complete self-reported evaluations of the CS plus and the CS minus. So the design is between subjects because we varied identity of the CS plus and the CS minus. So basically in the EC procedure we had one of two conditions which corresponds to one of two different files that participants were exposed to. So one of the EC files was, CS1 is the CS plus, and then the other CS1 is the CS minus. And we also have counterbalanced order of the blocks within the IAT, which is also done via having different scripts. So the IAT order 1 was in one script, and IAT order 2 was in another script. Why am I telling you these were different scripts? Because when you have different scripts, you get different data files. So in some contexts, you might need to derive the order that participants completed the blocks or which condition they were in based on a single data file with maybe a column that tells you. In other contexts, you have to basically integrate two data frames that have that came from those different conditions, and then mutate a column that basically reflects this information. So in total, we'll have 6 files. One is for the demographics, 2 for the EC procedure, which correspond to which condition they were in, 1 for the self-reported evaluations, and then 1 or 2 for the IAT with the 2 different block orders. So we've got 2 different observational units in the study. We have group level data, which we would like, or participant level data. So basically, where one row is equal to the values or observations for one participant. And we also might want to get trial level data. So where each row is equal to one trial from the IAT. For example, if you want to do some multi-level modeling, which I'm sure Medellin probably wants to do all the time. So these are what we want to get out from our processing. And so we want 2 corresponding process data files, one which reflects the group or participant level data, and one which reflects the trial level data. So given this, I've done it already in a processing script which I've provided on the OSF. Ideally, I would like to go through it quickly here, but I don't know if you'll be able to see. So I'm going to try and see what happens. I probably should pick a better color scheme. But okay, hold on. Let's see.
Make it bigger.
Yeah, I'm going to try to. I also want to make the other windows smaller. Like do this to make it tiny. And is it Command plus? I
Yes.
think?
At least in EC is Control plus, so probably Command plus.
Okay, I'm actually going to try Control plus. Oh, that looks like it did something. Yeah. Awesome.
Much better.
Okay, cool. So, can people see this? Should I make it even smaller or make it even bigger? No, smaller. One more. Let's go one more for a laugh. Okay. I hope this is clear. If you can't see and you want to follow along, the script is on the repository. It's the script that's called processing.rmd. So I guess I'm just going to kind of push through it for 10 minutes and then we leave 5 minutes for questions.
So this is an R script?
It's an R Markdown script.
Markdown.
Yeah, yeah. So immediately, yeah, because you can see immediately I've got these code chunks here that basically are the different paragraphs of the code. And I've tried to comment it as clearly as possible. So I basically comment each chunk at the start to basically tell you what the chunk is doing. And I also leave comments in this ugly purple in the code chunk itself. So what we do here is, okay, the first thing that we do, well, you always get this kind of aesthetic thing by default. This basically tells Markdown what to do when you knit. We can ignore it for now. So the first chunk, basically we're loading in the packages and the data. So in this case here we go, okay, well, load in Tidyverse because that's the only thing we need. and load in the data. So the data that we have, we load in the demographics file to a data frame called demographics raw df. The different two IAT data files are loaded into data frames called IAT competent NIFItes first, or raw df. So basically, NIFItes and LUPItes were the CSs, and warm and competent were basically the traits that were attempted to be conditioned. So I'm just giving these data frames informative names, so that if somebody comes along and they download my script, when they look through this, they can immediately see what these data frames are. They don't need to see IAT underscore C underscore N underscore F or something like that, which often people do. And actually you can see the data file itself is called that. So it's called IAT underscore CNWL raw. For this to be interpretable, you need to know that C stands for competent, N stands for NIFItes, W stands for warm, and L stands for LUPItes. And you have to understand that this is named based on the order that was presented in the IAT. Compare that to the name of this data frame, it's immediately clear what this refers to. And if you can come up with clearer names, then call it something clearer. Okay. I'm also immediately mutating a column in both of the IAT scripts called block order. The reason I'm doing this is because in this case here, this is IAT competent NIFItes first, so I can just say NIFItes competent first was the block order in every single observation in this data file. And likewise the same here, but with NIFItes warm first for the other data file. The explicit ratings and the EC data are just loaded in normally too. You'll note that here I have named this EC training condition 1 and EC training condition 2. In the case of this study, the specific identities of the conditions don't matter, as in what participants saw. We mainly just want to show that there are differences between the two. But if you want to give more meaningful names, like say condition underscore NIFItes competent, that's also very okay, as long as it's informative. But basically the only thing we're going to do with these data files is use them to identify which condition participants were in. Okay, so very first, let's process the demographic information. So let's just, load in the data. I'm going to run this chunk. That's also a handy thing about our Markdown. You can run individual chunks without needing to run the full script. So if you've got parts of the, it's not running, which is just great. What's up? Okay, it's running now. Okay.
Okay, yeah, that's fine.
Awesome. Awesome.
I was wondering what was happening.
Yeah, so I lied about our Markdown. It doesn't exist, and I just made it up. And I just broke the whole thing.
But you have an old version of R there.
Do I?
Yeah.
Oh.
6.0.
Well, don't tell anyone. It's updated. Okay, I'll tidy this back. Oh, hopefully we run now with limited errors. Okay, this should run, even if it's a bit slow. I'm going to go and update this immediately afterwards. Okay, so we've loaded the data files in. So let's have a look quickly at the demographics raw df and see what we're dealing with. So you probably recognize this. This is probably exactly what your scripts from or your data from Quizz look like too. So you get like a bunch of information like the date it was completed, the time, this group column, which in this case doesn't have any meaning. It's just the same as the subject entry, and the build, a bunch of stuff. But the key things that we want here are that we want to get the subject information, the response for their sex, and the response for their age. We don't really care about how long it took them to give these responses. We don't care about the build. We don't care about anything else. We just want these three columns. So what we do is we are taking the demographics raw df, assigning it to a new data frame called demographics. So basically getting rid of the raw part, because this name should be informative, and this is going to be my final demographics data frame. And then we're just going to select the relevant columns while also doing this rename thing. And then I'm also just mutating all of them as character, so all of the columns. The reason I'm doing this is because I'm going to want to join a couple of data frames together at the very end of the script, and sometimes R can get confused about the. So, for example, with subject, in one column it might, in one data frame it might think that subject is a numeric entry. In another data frame it thinks it's a factor. In another it thinks it's a string, and this can confuse it and stop it from being able to join the column or the data frames together. So I'm just mutating them all as character to avoid that issue down the line. So if I run that, the demographics file I get back, it looks like this. So in 3 lines of code, I've got everything that I need here for the demographics. I've got the subject, the sex, and the age. And realistically, I only needed this 1 line of code. This was just a little extra thing that I need for down the line. So pretty handy, I think. So let's go on to the explicit ratings. And let's have a look at what this explicit ratings data frame looks like. Okay, we've got basically only 3 things that we're interested in again. We've got the subject column, the response for a question about the relativeness of 2 CSs in terms of their competence, and then also one on the relativeness of the 2 CSs in terms of their warmth. I don't care about how long it took them to emit this response. I don't care about anything. I just want to know for each subject what was their response on these things. So actually, what I'm going to do is, well, firstly, there's something to note is that we've got, because of this ideally shouldn't happen if you code during Quizz script in a way that will give you data that you want to analyze. But in this case, we have not only just the entry for the rating, but also this like equals and then a big string that tells us what that score meant. Ideally, you should know that in advance. But if you end up with something like this, you're obviously probably going to want to get rid of this excessive string so that you can just use these numeric values in a regression. So the way to do that is, okay, we firstly select the columns that we care about while also renaming them to have slightly more informative names. And then we're going to use mutate to change the entries and data types for, oh, that was silly. Sorry, you can get rid of this. So just change the entries for those columns. So we're basically just going to get rid of the extra content and just return this single numeric value. The way to do that is to use the stringer package, which is basically a package in the Tidyverse for dealing with string data. And what we're going to do is use string sub. And what this basically will do, if we feed 1 as the start argument and 1 as the end argument, it'll just basically return the first character of whatever column we specify. So here I'm saying, okay, warm rating, which is the column that we already have, is equal to, and then the first character of warm rating. So we do that also for the competent rating. And then we say, okay, and the rating difference score is equal to the difference between the warm and competent ratings. And that's just basically what was pre-registered for the analysis of this study. And then I mutate all this character at the end for that joining issue.
But does it work without class numeric code?
It does not. I wanted to see if it would. Oh, no, actually it might. So sometimes...
You have a difference there.
Sorry?
You have a difference there.
What do you mean a difference?
In the following line, you are calling warm rating and competent rating as numbers.
Yeah, indeed. So sometimes mutate, when it's given specifically string data, mutate can interpret it as numeric. It basically sees what you want to do and it knows, okay, you want this to be numeric. Now, ideally, yeah, originally I did have it as numeric, but if I can avoid saying that, then I would like to. Also because immediately after I'm mutating all of them into character, and for me it just feels superfluous or something, but yeah. We can just run it like that and it'll work. Okay, so now we get the explicit ratings df, so not the raw one, but the actual one, and it has all that we wanted to know. It's got the subject ID, the ratings for warm and competent, and their difference. Okay, so we're basically coming to time, I'm going to, okay, I've commented the script so that in principle you can work through this yourself, and it should be clear. I'm also happy to field questions. I guess I'll just talk for another 3 minutes and then shut off. Okay, so we're going to try to do very quickly the trial level data for the IAT. So you can see I'm still commenting this. I'm using this level 1 heading to say the IAT data, and then within that this level 2 heading that says, and then we're looking at the trial level data. So we just want to tidy up the IAT trial level data for use in mixed effects modeling. So I'm going to try to run basically a function called bind rows, which basically binds the rows of 2 data frames. So if I say bind rows, so take this data frame and then bind rows with this other data frame, it's going to just basically try to put them together based on their rows. But if I do that, I'm going to get an error. And why do I get an error? Because, well, let's read what the error says. It's basically that issue I mentioned before about the different data types. It can't combine the response column called, the column called response from one data frame because it sees it as a double type object with the column called response in the other data frame because it sees that as a character. So the handiest thing to do is basically just mutate all of the columns into strings, and then if we want specific data types afterwards, we can re-mutate them back in. The first thing we want is just to get everything all together. So how do I do that? And I'll say this last thing and then I'll stop because it'll illustrate one final point. I'm going to take this first data frame, and then I'm going to mutate all of the columns within it with as character. And then I'm going to bind that with the rows from this data frame after it's been piped to mutate all as character. So not only can you use the pipe as a kind of line break for the sentence that is the manipulation of the data frame, but you can also integrate it within other functions. So this is really, really handy because it basically means that otherwise what I might have to do is I might have to take one data frame and then mutate all as character and save that to an object, then take another one and save that to an object, and then put them together. With this I can do it in 3 lines, and it's super simple, super straightforward. And just to show that it does work, I'm going to go, I need to make sure the comment's in that. Sorry. I don't want the pipe to be caught in it here because otherwise it expects for something else to happen. And you can see it works. So I get my trial level cleaned data frame, and well, yeah, there's several thousand rows, but basically it's the 2 joined together. Okay, so I'll stop here. There are more handy tips and things like that in this sample processing script that I've given, but I hope I've convinced you that the organization of a project is important, and it is equally as important to data processing as the actual code that you will write, because that's where it starts. And I hope I've convinced you that our Markdown is at minimum cool and at best better for reproducibility, which is, in my opinion, the most important thing, and that the Tidyverse is the best thing that's ever been invented. So thank you very much, and if you have any questions or anything, please just let me know.
I would use an extra minute maybe from the break if you show us how do you combine them files. So after you do all this.
Yeah, okay, so to flag then basically what I'm doing, I think everyone figured it out probably, but what I'm doing is basically creating a bunch of different data frames that all have the same observational unit, which is subject. And then at the very end, what you can do is you can use the function called left join. So what left join does is it takes, say, one data frame, and I'm selecting some stuff here, and then it takes another data frame and joins it from the left. So here I'll end up, if I just run, say, this, I'll end up with a data frame called participant level df, which has the columns subject condition dscore from this, and then all of the columns from IAT's exclusions df. Does that make sense?
Even though I find extremely annoying that they never have some function that you give all the data frames that you want to merge as arguments,
yes.
it does it.
That's, yeah, if I could like do a fork on GitHub to complain about this function, I would say that. Or even that you could feed them as like a vector of names or something, but yeah, it doesn't work. Yeah.
So you've done everything in R Markdown now. Would you do your analysis there too then also?
Yeah.
So you don't use RStudio anymore?
No, so R Markdown is a type of file that opens within RStudio. So RStudio is like the interface that opens a bunch of different types of files.
So it's differently organized because when I opened it, the script was on the other.
That's actually just, I changed that because I prefer to have the code on the right hand side.
Okay, so
but
you
it's
can switch it around.
Yeah, exactly. You can change the windows and stuff, but it's exactly the same environment. Relatedly, if anyone's ever interested, you can also write a bunch of different types of code in R Markdown, like Python or SQL files. And there's also a package called, I can't remember, I think it's Reticulate, and Reticulate basically lets you run both R files and Python files in the same set of code chunks, which is very handy if you're doing like, deep learning with TensorFlow in Python, but you want to do your processing in dplyr.
Can you show the link, the OSF link?
Yeah.
I also put the OSF link inside the folder that I gave you last time, so there is a.
Awesome.
You can just upload everything to the OSF.
Yeah, everything. That's my personal repository that I made for this. Is there also like a project or like is there a OSF link for the whole LEARNVUL project? Or?
No, I just use my Dropbox, but maybe I can just upload every slides by all the speakers on the OSF. It will be more fun.
Yeah, we'll share that.
Okay, thanks everyone.
Yeah.